First of all, thank you very much for giving an opportunity to present our results, especially today on 7 September, because yesterday evening we celebrated our new Jewish year with families. And so, in advance, forgive me if I will be not exactly correct and precise as I want. So today, I want to present you results of our experimental, theoretical, and computer simulation research which we did during the last few years in our plasma and pulse power laboratory in physics department Technion. And here you may see the list of our PhD students and my friends and colleagues who are participating in this research, as well as with Vladislav Rostov, who helped us a lot at the beginning, and not only at the beginning of this research from Institute of High Current Electronics. And below you may see a list of publications which we published so far on this subject. Okay, motivation was very clear for us. We want to understand physical phenomena which could accompany interaction of very short duration, sub-nanosecond duration, microwave pulse with extremely high power of hundreds of megawatts, even gigawatt, with neutral gas and preliminary formed plasma, because we think that this could be as a scaled up experiments to the femtosecond, even powerful lasers interaction with gas and plasma. And I will talk about this a little bit later. In fact, many years ago, more than 30 years ago, in the Institute of High Applied Physics in Nizhny Novgorod, which was Gorky city at that time, scientists Bogolyubov, Lawrence, Semyonov, and Sergeyev already showed that in the case if someone will have very high power and short duration microwave beam, it could be possible to obtain self-channeling of such microwave beam. Another thing, and this is what you see on the left side, this is the propagation of the microwave beam through the neutral gas, and this beam by itself produced a plasma channel inside which it's propagated. And the physics behind this I will say a little bit later. Another thing, on the right side of the picture, you can see that this is the modulation of the density of the plasma, when microwave beam with such density propagates through the plasma and it's leaves behind it wake field. This means positively and negatively charged region of the plasma. And why it happens, I also will talk a little bit later. So there are several interesting phenomena which can be studied using such microwave beams. I am not talking even about things related to how ionization process occurs during extremely short times within a frame of the microwave beam with electric fields much larger than hundreds of kilowatts per centimeter. So in our laboratory we understand that the best chance is to use backward wave oscillator operating in super-radiant mode, which was developed in Nizhny Novgorod and in Institute of High Current Electronics, and also in experimental research in Institute of Electrophysics. And this source can produce really such high-power microwave beams which we need. And these experiments really can be considered as scaled up in time and in space as compared with powerful, extremely short laser pulses, where we have difficulties to diagnose plasma during the interaction of such laser beams with plasma and neutral gas. In our experiments, we are using two basically setups. One setup you may see here, this is high voltage generator, similar to what Sergei Rukin developed, well developed in the Institute of Electrophysics. This is our homemade generator on 320 kilovolts, 5 nanoseconds. It's supplied pulse to magnetically insulated diode where we produce 2 kiloampere, around 2 kiloampere electron beam, and which propagates through the slow wave structure, immersed in the solenoid, producing in this system 2.5 Tesla with 10 millisecond period, half period. And after that we have mode converter from 01, TM01 to TE11 mode. And finally, this pulse is radiated through the antenna with power around 500 megawatt, 0.5 nanosecond half-width full max, and frequency 9.7 gigahertz. And using this spherical lens made of ultim, we focused microwave inside this chamber, which filled by the gas or preliminary formed plasma by RF discharge. And later, using different types of diagnostics, we characterize the propagation of this microwave beam and plasma which is formed. We used different gases, argon, helium, and plasma density was measured very accurately by using different methods. Another setup you may see here, this is the same pulse power generator, only the structure is different, slow wave structure I mean. Now we are producing around 1.2 gigawatt pulse with 0.8, really it's even less. Here is full duration on half full wave's mass, this is around 0.5 nanosecond, and frequency 28.6 gigahertz. This pulse propagates inside the waveguide, which you may see here, and we are measuring by the directional coupler incident and output pulses at the output of this waveguide, which also has slots. Why slots? Because through these slots, these slots are used to make pre-filling of this waveguide by the plasma produced by flashboards, which are placed at the outer side, inner side of this tube. Using one small spectroscopy, Lambert probes, microwave cutoff, microwave interferometry, which actually routinely we are using in our laboratory, we characterize this plasma and therefore injection or generation of this microwave beam in injection into the preliminary formed plasma using time delays between plasma formation and the microwave beam generation. We do know the plasma density. Also here, as an example, you may see here the electron beam pattern on CR39 target. In the case of 28 gigahertz, this beam should be very, very precisely aligned in the slow wave structure in order to have good coupling. And the thickness of this beam is around 0.2, 0.3 millimeters, not more. And the magnetic field in this case is around 8.5 Tesla. Now, as a diagnostics, as I told you, we're using electrical ones, which are listed here, plasma light emission just qualitatively, and this is fast framing photography, single or multi-frame with frame duration down to 0.7 nanosecond, plasma density, I already told you how we measured, and microwave characterization, this is directional couplers, calibrated antennas, and pattern of the microwaves using arrays of neon lamps. Fast electrons and X-ray detection, for this we use scintillator coupled with optical fibers and with fast photomultiplier tubes and Faraday cups. But in fact, Faraday cups doesn't work in this noisy environment. And for wake field detection, we're using probing DC electron beam with fast scintillator, less than 0.7 nanosecond decay, and a strict camera. And data acquisition with digitizing oscilloscope having good enough bandwidth. Now, some results. Regarding results, we can say I will start with 9.6 gigahertz, and using mode converter, we transfer from TM01 to TE11 mode, and here you see that this is rather good pattern of the electron, of the microwave beam with this pattern corresponding to TE11 mode at a distance of more than 1 meter from the antenna. This is how looks spatial distribution of this microwave beam, also at the same distance. And typical, in fact, this is not typical, but always we have rather good reproducibility of this microwave beam generation. And this is the instantaneous and average power and electric field of this beam. So, in fact, this BWO is able to generate in very reproducible manner microwave beams with 550 megawatts, and parameters are listed here. And moreover, the power of this microwave beam is almost even a little bit more larger than 50% than the power of the beam. This is really super ideal mode of this microwave beam generation. Now, let us talk about physical results. For us, it was very, very surprising when using spherical lens, which you see here, in these first frames you don't see it. We obtained that beam is not only focused microwave beam, because what you see here is light emission of the plasma which microwave beam produces in neutral gas. In this case, this was air at 7 ton. And you may see a rather long plasma channel, which is produced by the microwave beam. So what we see, instead of diversions after the focus, beam continue to propagate in some self-produced plasma channel. And this is the snapshot of ionizing channel. Moreover, using front view of the observation of the plasma channel, we were lucky, and in few shots we obtained that there is almost no plasma inside this plasma channel, or let's say emission of the plasma inside this channel, and bright emission at the periphery. The same results we obtained when we worked with preliminary formed plasma. We also obtained very long channel with many times larger relay length expected for our case. Another experiments with neon lamps, which we placed inside this Pyrex chamber filled by the gas, showed us, for instance, here you may see in vacuum case, this is for helium gas, and this is for air. And in helium gas, you may see that at some pressure, only central emission of the microwave. So microwaves propagate only close to the axis. And at some pressure, opposite, there is almost no emission from the center from these lamps, and only at the periphery. The same things we obtained in air, of course, at other pressures. it was proof that this microwave beam by itself produced plasma channel. And how it's going, you may see in this LSP simulations. Okay, I will try to move it. So what you see, the density profile and how microwave pulse is propagated in z direction. And you see that at the periphery, there is a dense plasma formation, and at the axis, there is almost no plasma formation, which allows microwave beam to propagate, because at periphery, plasma has density larger than critical one for this microwave frequency. Why it is such? Explanation is very simple. When we have so high power microwave beam, electric fields at the center is extremely high. Therefore, oscillatory energy of electrons is also high in the center and much higher this energy than energy electrons at the periphery. However, the ionization cross-section has opposite tendency. It's larger for low energy electrons and smaller for high energy electrons. So therefore, density of the plasma produced at the axis close to the axis of the microwave beam is less than the density of the plasma produced at the periphery. And this is what we call self-channeling of the electron of the microwave beam in the self-produced plasma channel. Another interesting phenomenon which we have obtained is the compression of the microwave beam. And this you may see here. This is the duration of the microwave at some certain pressure, because this is the pressure of the gas and this is full width half max of the microwave beam, and you may see it decreases. And simultaneously at that conditions we have increase in the power of the microwave beam. So at some condition one can obtain that microwave beam having some certain time duration when it's propagating through the plasma or gas can be compressed by itself. Why it happens? It happens because due to very high electric fields, let's say gradient of the electric fields, which causes Vandermote forces, plasma density in the frame of the microwave beam changes, and this leads to the change of the phase velocity and correspondingly to the group velocity of the microwave beam, leading to the compression of the beam which propagates through the plasma. Another interesting things which we obtained is related to high energy electron beams. We obtained, as I told you, all our efforts to work Faraday cups failed, because even we have double, triple screening of them at the microwave noisy environment, it was almost impossible, I think, to use them. So we used the coupled method with optical fibers covered with scintillator and aluminum foil in front there. Different thickness, of course, aluminum foils. We obtained axial accelerated electrons. And the radial accelerated electrons with energy in axial direction up to some certain plasma conditions, of course, energy up to 100 keV, and in radial directions of tens of keV. And this also proves that we have huge Vandermote forces which push electrons outside of the region of the plasma, and formation also of the wave field. But this is not yet direct proof of the wave field formation. I will talk about this later. Moreover, what is interesting, and I will talk about this, due to pushing of the electrons output of the plasma channel, we can generate or we can form positively charged plasma, purely positive plasma, which I think very difficult to make in other conditions. Please look here on the simulation results, how, sorry, what do I have to do? I have to, okay. So what you can see here, propagation of the microwave beam and in Z direction, and fluctuation of the density of the plasma in cross-section in a radial direction and azimuthal, because this is 3D simulations. And you clearly see here wake formation after the beam is propagated, which give us oscillation of the electrons in positively charged plasma. For instance, here you may see what's going on when microwave beam propagates. It's leaving positively charged plasma, and this is the non-disturbed plasma. In these snapshots, you can see EZ electric fields between inside the wake field, and here the electric fields in radial direction. Now I will move to another very, I think, exciting results recently obtained in our laboratory when we obtained nonlinear absorption, full absorption of this extremely high power microwave pulse in plasma field waveguide. So this is the same experiments I explained earlier. You may see flashboard system, waveguide with slots, some diagnostics, fibers with scintillator. This is how microwaves is coming from the generator and radiating outside, two couplers, incident and output, and the different types of diagnostics. Once more, also in these experiments we obtained energetic electrons in radial and axial directions, but this is not the point. The point is that in these experiments we obtained something which we at the beginning cannot explain, but now we know the reason. For instance, here in black you may see incident pulse. I mean normalized power. And this is experimental results. And this is the transmitted power of this microwave pulse. And the difference from A to D is in the plasma density, nothing more. And what you see that increasing the plasma density leads, as expected, less and less transmitted pulse, and after that we do not have no transmitted, no reflected pulse, because this is reflected pulse when plasma density becomes larger than critical one. Where the pulse? How is going? Who observed this? Or who take it from the system? No back, no transmit. What you may see here, this is the transmission and reflection coefficients. This is the transmission coefficients, and this is the reflected coefficients. This is experimental data, and this is simulated data. So solid is simulated data, and dash is transmitted. They are more or less have good agreement, except, let's say, absolute values. But what is the point? That at the same plasma density, they showed that all the pulse is absorbed in the plasma. No transmission, no reflections. Now, thanks to Dr. John Leopold, who is doing all these complicated simulations, 3D simulations, we understood the physics behind it. And also the same was predicted by the model suggested by Yuri Gleev. The point is the following. What you may see here, the same a ratio of the transmitted to the reflected pulses at different plasma densities, and at some plasma density no reflections, or let's say almost no reflections and transmission. And the reason is that at that conditions, almost all energy of the microwave pulse is transferred to the energy of oscillating electrons, and they translate this energy to the plasma due to collisionality. The same you may see here as a time evolution in Z direction of the pulse propagation. When it's coming into the plasma, this is plasma distribution, it changes and finally disappear. Now I will just repeat what I told. When pulse, microwave pulse, is going inside the plasma due to conformative forces, part of the electrons leave the plasma, and we have formation of the positively charged potential well. In this potential well, remaining electrons are captured and they oscillate and take energy from, they oscillate in the high frequency electric fields of the microwave pulse, which group velocity decreases significantly, approaches zero, but not really zero, of course, because we're still working below critical density. But because existence of this pulse inside the plasma started to be several nanoseconds, remaining electrons have chance, due to Coulomb collisions, transfer their energy to ions. And this is how going this physical process, non-linear of course, of the absorption of the microwaves. We checked that this effect does not occur at low power of electromagnetic fields, and such complete absorption has not been observed before for high power microwave pulses in any other circumstances. And the last things which I want to present you is related to real-time plasma wave field direction measurements. This is our dream and our purpose, and in fact we already succeeded in this. I just cannot show you experimental results, we are still analyzing them, but I hope you can believe me, we do obtain direct measurements of the wave field formation. In these experiments, you may see the same waveguide with slots, and here we developed our homemade Pierce electron gun, producing us very precise, around less than, let's say not less, 1 millimeter, around 1 millimeter electron beam with current around 0.1, 0.2 milliamperes, which transfers the waveguide through the slots in transverse direction with respect to the propagation of the microwave beam. And here at the back side we have fast scintillator. Once more, time decay is less than 0.7 nanosecond, which allows us to obtain wave field. What is the idea behind this experiment? Very simple. When we have wave field, we have Z-directed electric field. In this case, electron beam which is transferred to Z direction, should acquire some deviation. And this deviation we can see on the scintillator, which is produced photoluminescence, which will be captured, and this is what we are doing by our fast streak camera with time resolution of around 20 picoseconds, even less, 10 picoseconds per pixel. It depends, of course, of the streak time. We are working with streak of down to 100 nanosecond, and this is 30 picoseconds per pixel. Now, once more, wave field formation, and what you may see here, and I will show you this movie, is the microwave pulse propagation. At that figure, you may see the density evolution. Here you may see electron beam in propagating towards the scintillator. And here you may see the image of the electron beam on the scintillator when microwave pulse propagates. Okay, now please look on this movie, and this is in fact what we already have obtained by our strict images of the beam. Beam sometimes even disappeared, and after this, once more, it disappeared. You may see formation of the wave field, and you may see deviation of the electron beam on the screen. So this will be, I think, for the first time, direct, straightforward evidence of the wave field formation using such high power microwave beams propagating in the preliminary formed plasma. Okay. Now, so far, what we have now as a conclusion, I will say, we have obtained, predicted more than 30 years ago, ionization-induced self-generating gases and plasma gas mixtures. We obtain pulse frequency shift and pulse compression due to decrease in the density of the plasma in the frame of the microwave beam propagating through the gas of plasma. We obtained very exciting complete absorption of the high power microwave pulse in plasma with density below critical density due to nonlinear effect I explained you. High energy electrons also have been obtained, and this relates to the formation of the wave fields and conformative pushing of the electrons. We have obtained formation of the positively charged plasma, which can explain also complete absorption of the high power microwave. And right now we're very close to complete our research of observation wave field in the cylindrical waveguide. So we expect to observe other phenomena not seen before using these unique experimental setups. Thank you very much for your attention and patience.
Thank you.